Welcome to today's notes. So today we're looking at the notes on equipotential lines. So these should be pretty straightforward. So equa means equal, potential means potential. So we're talking about lines of equal voltage. So let's dive right in here. So here this talks about the electric potential in a capacitor. And we start off looking at the parallel plate capacitor here, and you can see a very similar picture to what we've done before. We said, okay, we got charge on each plate, and here we're starting with a positive charge, and we're going to use work to push the positive charge towards the positive plate. So here this just says, okay, yeah, we have an electric field. So if we choose electric potential energy to be zero at the negative plate, then the charge's potential energy at any other point is equal to the amount of external work required to move the charge from the negative plate to that position. To move a charge to the right at constant speed, the electric field must be pointing to the left, and the external force must push to the right, so the force of the hand equals QE. So the work done to move the charge is force times the distance. So in this case, the distance is the x distance if we're moving in the x direction. So the electric potential energy is equal to the work, which is equal to QEx. So before we go too far here, I want to go back to this picture. I thought another picture was coming up. So here you can see we were saying, okay, we set the potential energy at this plate to be zero, and then the work is done to go from zero to anywhere else, okay? So that's what it's giving us so far, and so we said, okay, if we move it from here to there, it's over this distance x, and so we take the work, which is force times the distance, and so we said the force is equal to Q, the size of the charge, times our electric field, right? So that would be equal to the energy stored here, so it's QEx. So that's what we got right here. So the electric potential of a parallel plate capacitor at position X, measured from the negative plate, is V, because that's electric potential, not electric potential energy, so we just divide by Q. So if U was QEx, we divide by Q, well, we get V is just EX, okay? So then that, we use into that equation another substitution. E for the electric field is Q epsilon naught over A. And it says the electric potential increases linearly from the negative plate to the positive plate. Right? So X equals 0 at the negative plate, X equals D at the positive plate. So the potential difference, V sub C, between the two capacitor plates is, go away. V sub C equals V minus V, which is equal, those are two minus signs in there, which is equal to ED, right? So in many cases the capacitor voltage is fixed at some value, V sub C, whatever that voltage is, and by connecting its plates to a battery with a known voltage, we can get that V sub C. So the electric field inside the capacitor is equal to E VC over D. This means we can establish an electric field of known strength by applying a known voltage to a known spacing. So I know that this wasn't very clear here, but basically we derived this equation and we derived that next equation, and we're going to combine them here in a second. So that was the purpose of going to this. So the electric potential inside a position X of a capacitor is V X over D delta VC. So now this is an equation I think is obvious, but if it doesn't come obvious to you, write it down, okay, and think about it. But this should make sense that if we have 0 volts at the negative plate and you go all the way to the positive plate, you should have your total voltage, whatever that happens to be, V sub C. So if you're at x equals 0. Well, the 0 divided by anything is 0, so this voltage would be 0. So we're just making a ratio of x being the partial distance and d being the total distance. So obviously if you know the total distance, you get the total voltage, zero distance, zero voltage, half distance, half voltage. So here it says we have a graph of potential versus x, and so again this is just what we're talking about here. 0, 0. So at x equals 1, you get half a volt. At 2, you get 1.5 volts, and 3, you get, 2 was 1 volt, and 3 was 1.5 volts. So that's assuming that we have a distance of 3 millimeters between one plate and the other in this case. And there's a lot of equations here that we've hit so far. We'll see how they're a little bit more related. We'll do some substitutions here in a second, but this isn't quite as bad as it starts off. So a three-dimensional view. So if we go from 0 volts to 1.5 volts, we have what are called equipotential surfaces. So equipotential, equal potential surfaces. These are mathematical surfaces, not actual surfaces. Like the plate, the positive plate and the negative plate are actual surfaces. So you could say the surface plate is 1.5 volts and the negative plate is 0 volts. Okay, those are physical surfaces. But these that are marked like 0.5 and 1 volt are not actually there. It's just a mathematical plane. It's okay, everything in this plane is half a volt. Everything in the 1 volt plane is 1 volt. Okay? So they all have the same value of V at every point. Okay, so if you have a parallel plate capacitor, well, the equipotential surfaces will be nice parallel plates as well. And so equipotential surfaces are very similar to lines on your, what is it called, topographical map. So if you've ever seen a map, like it has like the height lines, like the contour lines of like a mountain and a hill, it's very similar to that. So if you think about gravitational potential energy being mass times gravity times height, well, that would be gravitational potential energy. So let's look here at this. So think about, okay, we've got gravitational potential energy. So think about the Earth. Okay, so you've got like a hill, right? And so, well, here, let me back up. So you got gravitational potential energy, U sub G, is mass times gravity times height. And we talked about how electric potential energy, U sub E, is Q, E, well, D or X, however you want to say it. I'm going to say X. And we got to voltage because U, E divided by Q. So that gives me EX, okay? So here we can get to something similar if we divide both sides by M. Now this doesn't have an equivalent in gravity, but you'll see in gravity that would give us GH. And so G being similar to the electric field, so G is like our gravitational field, H is our height, X is obviously distance. And so you can imagine like on a hill here, we know that like a ball at this point would have a certain amount of gravitational potential energy, and at this point it would have more. So you don't need to know the mass of the object to know that the higher it goes, the more gravitational potential energy it will have. But even over here on this side, if you're looking at this, you go, okay, well this would have the same gravitational potential energy as that, and this thing over here would have the same gravitational potential energy as that. And so we could say that these two are on the same height, right, the same level surface. And so like this contour line here would be an equipotential surface for gravity, and likewise one for this. And so that's what we're trying to establish here. But the equipotential lines for Earth, or for this parallel plate capacitor or whatever, yeah, they're rectangles or whatever for this capacitor because our plates are rectangles. But again, depending on your charge distribution, so if I just had like a positive charge here, my equipotential surfaces would be concentric circles. And so that's what we're going to look at, is we can figure out how to write down these equipotential surfaces. Because when we're looking at these equipotential surfaces, they're going to, once you figure out, okay, this surface has 10 volts, this thing is a height of 5 meters or whatever, then it's going to be really easy to jump to electric potential energy, or electric potential, well, not electric potential, but jump to other things that we want to find. So here, this is just simply another viewpoint of the same thing. So again, 0 volts in your negative plate, 1.5 volts in your positive plate, and we can see the equipotential surfaces. Most of the time, the way I'm going to draw it is going to be like this. Although these previous pictures, this one and even this one, are expressing the same thing. So you got to understand, this graph, this 3D picture, this 2D picture are all trying to express the same thing. It goes from 0 volts to 1.5 volts, and it's nice and evenly spaced. Some of the pictures you'll see on problems and stuff, if they're made by a set of charges, these equipotential lines could be just anything, okay? So you're going to have to look at the distribution first to kind of decide what happens then, okay? So it says we call these lines of constant equipotential, call these lines of constant equipotential, or simply equipotentials. So let's look at this question here. It says we have a parallel plate capacitor. Is constructed of 2 discs spaced 2 millimeters apart. It's charged to a potential difference of 500 volts. So we have this thing is 2 millimeters, and we go from 0 to 500 volts. A proton is shot through a small hole in the negative plate with a speed of 2 times 10 to the 5th meters per second. What is the farthest distance from the negative plate that the proton reaches? So it's going to be shot in here, going the speed. It's going to slow down, stop, and turn around at some point. So we want to find this final position. So if the voltage is equal to QE, we're going to find that XF. So we're going to find the distance that it stops at. So it should be less than 2 millimeters. And so here I'll just kind of work through this with you, that this is just a conservation of energy problem. So if you go back, I'll go back here. So when it comes in, it'll have a kinetic energy, right? It doesn't have any electric potential energy, like gravitational potential energy. It starts kinetic, and then when it stops, it will all be electric potential. So you say, okay, kinetic plus potential, this is, final should equal my kinetic plus potential initially, right? It's conservation of energy. Well, my final, I don't have any kinetic. It's all potential, and initially I only have kinetic. I don't have any electric potential. So then I can set Q. Now notice here I set Q times delta V X over D. So that's that formula we saw earlier, because we can express delta V, we know it's 500 volts. We don't know what the voltage is where it stopped. So we're just going to use that ratio we had earlier, that we know the voltage here will be some ratio of X over D. So again, if it only went halfway, then we have 250 volts. If it went all the way, then 500 volts, so on and so forth. So we can put this little ratio in here. We know that D is 2 millimeters, and it said it's a proton, so we know the charge, we know change in voltage is 500 volts. We're looking for X, so that's good. And then we do 1/2 mv squared. Again, we know it's protons, so we know the mass, and it gave us our velocity. So we plug it all in there, do some math. Hopefully you guys know how to do math. And you should get about 0.84 millimeters. So that is, again, significantly less than 2 millimeters. So, hopefully you can check that, make sure it works. To find the electric potential due to a single fixed charge, if we want to find the electric potential from one charge, okay, we must first find the electric potential energy when a second charge, is a distance away, and then we divide by the charge that we put there to find the voltage. So says we find the electric potential energy by determining the work done to move the second charge from the point where U equals 0 to a point where, R equals, or until a distance R from Q. So what this is saying is, we want to find the electric potential V, but before we can find that, we just have to find the electric potential energy, and then we'll divide by the charge we put there. So previously we said that the electric potential energy would be 0 at the negative plate. Well, in this case we just have one charge. We don't have any second charge. So how do we find it? So we set the electric potential to be 0, infinitely far away, and then as you bring it in, it's going to be basically negligible force up until a point, and then you do force over distance, based on the distance from our charge. So this is more similar to not being on the surface of the Earth in terms of gravity, but it's more similar to being like a planet or maybe a star out by itself, and you're bringing like a second star near it to see, okay, what's the gravitational force or gravitational potential energy between these two. Okay. So here you can see that the, electric potential energy is going to be basically 0 when you're infinitely far away, and then as you get closer and closer it'll be larger and larger. And so that's what the graph is talking about here, that when you're really far away, this force is going to be nice and easy to push it. And so if you're going to push it this certain distance, it's a small force, but to do that same distance when you're significantly closer is going to require more force, because it's not a linear force, right? It's based on distance. It's based on, Coulomb's law. F equals K, Q1, Q2 over distance squared. So we can't use work as force times the distance, because the force is changing with your distance, okay? So we can't use that. So in a more advanced class you would use calculus. We're not going to. So just be careful. So here it gives you an example. It says, what's the ratio of VB over VA of the electric potentials at the 2 points? So VB is over here 3 millimeters and VA is at 1 millimeter. So I don't think I gave you much time with the first question, so you can either pause the video and think about it, or I'll wait a second here. So here we're looking at the ratio of VB to VA. So the first thing you should think to yourself is, okay, well, which one is stronger? I see a 9 and a 3 and a 1/3 and a 1/9. So should the electric potential be stronger at A or stronger at B? Well, it should be stronger at A, so that should make sense. It's closer. And it's only about 3 times stronger, because it's, the voltage is KQ over R, not R squared or anything. So it's pretty simple that, you go 3 times further, well, you have 1/3 the voltage or electric potential at that point. So here are 3 graphs, just like we had 3 for the parallel plate capacitor. Here it gives us a graph of voltage versus distance. And again, it's not linear, so going from one point to another point, you're going to have to pay more attention, because, on the parallel plate capacitor one, it was just a straight line, so if you had the slope, you could easily calculate what was going on between them. Here you're going to have to pay, again, a little bit more attention, and I didn't go into much detail because it really depends on the question, so that's what the audit's for, to get some practice on questions. And then the second picture is a 3D image, and then the third one is just your 2D image, and again, I stick pretty much to these 2D images. One of the things that you'll notice here, that even on the equipotential map, it's still trying to express this curved relationship. And so generally each equipotential surface is how do I say this? Each equipotential surface will be a certain number, and the difference between them should be the same. So let's say that they're all just a whole number of voltage. So this could be like 1 volt, 2 volt, 3 volt. And so you'll notice that it gets further away as we get farther out because the force required is weaker the further away you get. And so it's not, these are concentric circles, but they're not equidistant from each other. And that's not a mistake or something. And so, like I said, these could be 1, 2, and 3 volts, or they could be half a volt, 1 volt, 1.5 volts, whatever. It's kind of like your scale on your map that, once you've established, okay, each line is going to be this much, well, then every line should be a multiple of that. So just kind of keep that in mind. You can kind of see that it's, obviously going to be hard to see this in 3D here. They had to make holes just so you can see what's going on inside. So I'm not a big fan of the 3D model, but if it helps you, it helps you. So, it is common to charge a metal object, such as a sphere, to a certain potential, right? So you use your battery, charge up your object, if it's just a metal sphere, then you're just going to be using the positive or the negative side. V naught is the potential at the surface of the sphere. So this is something similar to what we did for electric fields in the previous section. So V naught equals V at the surface, right? And so here, this gives us, it says Q over 4 pi epsilon naught R. Well, that's the same as KQ over R, because K is 4 pi epsilon naught. Hopefully you'll remember that. The charge for a sphere of radius R is therefore, so here, it just solve for Q, so you just move all that stuff over. And the potential of a sphere outside the charge potential V naught is, well, V naught and then your ratio. So you have R, which is the distance to the, I guess R is our sphere. So capital R is the distance to our sphere, and then lowercase r is the distance you're actually going. Which makes sense because the further away you get, well, the less voltage you should have. So, as it says right there, the potential decreases inversely with the distance from the center. So, what is the electric potential at the surface of the sphere? So I'll give you a second. So I think this is pretty obvious if you go back to this last formula here. V is big R over little r V naught. So we're solving for V naught in this case. And it gives us V is 30. It says big R is 5. So little r is 15. So, go back here. So if big R is 5, little r is 15. So you do 5 over 15. So it would be 1 over 3, but this is 1/3 V naught. So then you multiply both sides by 3 to get V naught. So 3 times 30 is 90. Suppose there are many source charges, right? You got charge 1, charge 2, you got a bunch of charges just hanging out in space here. So how do we find the voltage over at that point? Well, you just simply add up. You go, okay, from this point to here, that's V1, then V2, then V3, for every point, for each charge at this point, you just add them all up. And remember, these are not vectors, so positives and negatives, plug all that into the formula, and just add them all up, and you'll get an answer. And so here, it says voltage is the sum of K, 1 over 4 pi epsilon naught, as it says right here. Each individual charge divided by the distance it is away. And so positives would give you more voltage, negative would give negative voltage. So if you have a mixture, it's possible to have 0 voltage over there or anything in between. So, question 4. A proton is fired from far away towards the nucleus of an iron atom, right? And it says the iron atom contains 26 protons. Seems important. The diameter of the nucleus is 9 times 10 to the negative 15th meters. What initial speed does this original proton need to just reach the surface of the nucleus? Right? So we're going to assume the nucleus doesn't move. We're firing that proton in there. So again, I'll give you all a second, or I can pause it. Okay, so here is we got 26 protons, so we need to find the voltage at a certain distance away. So in this case, we said, okay, we're going to sum from 1 to 26. They're all basically in the same spot. So in this case, we said the distance is 4.5 e to the negative 15th. So the diameter of the nucleus is 0.9 times 10 to the negative 15th. So essentially, if you think about a nucleus, you have all these, let me just draw it. So you've got a nucleus here, and it's got a bunch of protons all up in there. But so this proton is like 4.5 away from the center, but this one is also 4.5 away from the center. So if the diameter is at 9 times 10 to the negative 15th, we're just going to pretend like this whole thing, if you get really far back, is just one point. We're pretending like all of them are just sitting here at the center. Obviously, as a proton comes in, it'll be closer to these charges than these, but these guys will push more, as it gets closer, and these guys will push less, which would average out to, everything being in the center, which is what this is talking about. So that's our distance, and so our distance is kind of like from here to the edge, okay? So that's the distance that we've chosen here at first. And it says, okay, well, the proton's fired in there, so we have K as 9 times 10 to the 9th, and our charge, we're just looking at our, not surface charge, our stationary charge is protons. We just plug all that in. So at the surface, we have a surface potential of 8.32 million, million volts, okay? So then we look here and it says, okay, QV, well, where does QV come from? Well, sorry, it's not just QV, it's QV equals K. So I feel like this is a conservation of energy problem, that it has some kinetic energy as it's fired in, and we're trying to figure out what that initial velocity is that's coming in with. And we go, okay, it's going to come in with kinetic energy, and it's going to stop just at the surface, which is where we got that distance, that radius distance, so it's going to stop right here. So we want to find the potential energy, U, at this point, and set it equal to K, the kinetic energy coming in, right? So U is QV and K is 1/2 mv squared. So we just found V, the charge, the potential at the surface. And so now K is 1/2 mv squared. So in this case we solve for velocity. So hopefully that's obvious what you see right here. And then we can see that that equals 1, you just plug in 2 times the charge. In this case, this charge is the charge coming in, which is again the proton, times the voltage divided by the mass of the proton, which should give us, let this thing go away. Yeah, so 39 million meters per second, which is pretty fast. We're up in near some speed of light, or a significant portion of the speed of light at this point. So we've already talked about nuclear physics, and so you can kind of think back that we talked about how, if you want the so if this is just a regular nuclei, just like one proton, it's not going to require something going this fast, but you can see how, like, as you add more protons to the nucleus, it's going to be harder and harder to get another proton in there. And iron is the point at which, when you're trying to do nuclear fusion, it actually requires more energy to force the next proton in than the energy you get out from nuclear fusion. And so hopefully this can kind of show you why. Like, even if you have that iron atom just sit there stationary, like 40 million meters per second, that's a significant fraction of the speed of light just to get this thing to like get to the surface there. So hopefully that gives you some thoughts back for that nuclear section of why iron doesn't work very well for nuclear fuel. So potential of many charges, and so we can have, one set of stationary charges, we have a bunch, and we can put things around. So here this gives you, like a positive and a negative, and these are equipotential surfaces. And so you'll notice exactly halfway in between we get a nice straight line for a particular voltage. In this case it's 0 volts because we have the positive and the negative are the same size. So, at which point or points is the electric potential 0? So, A, B, C, D, or E says more than one of these. So, I'll give you a second. So with this, you have to be careful here because this is not electric field or electric force, right? So there is no real direction. It's pretty easy, but again, don't think in terms of vectors. So in this case, it's more than one of these. So if we look through these, this is 2 positive and 1 negative. So here, it's KQ over R squared. So here in this case, we have 2 for Q. And the R for A would be 1, 2, 3. So this is roughly 2 over 3 for positive, but for negative, it's 1 over 1, 2, 3, 4, 5, 6. So 1 over 6, so those aren't equal. Sorry. 2/3 for this one would be negative 1/6 for that one. So I'm going to clarify. So this one for B is 1. So you got 2 over 1, so that would be 2. And so for this one, this would be 1, 2. So this is 1 over 2, so those are opposite, so no. But C is interesting because you have 1, 2, so this would be 2 over 2. So it gives us a ratio of 1 for the positive charge. And so for the negative, you get 1 distance over, or negative 1 charge over 1, so that would give me a negative 1. So these two would cancel out at C, right? And that's where it's very similar to the electric field, because you're like, oh, it's this distance, blah, blah, blah. Okay, fine, but let's take a look at D. So for the positive, you go 1, 2, 3, 4, 5, 6. So that would be 2 over 6, so 1/3. And this one would be negative 1, 2, 3. So negative 1/3. So D also cancels. So it's both C and D. So like I said, I don't think these are terribly hard. I mean, you just plug in, there's not much thinking, but you gotta be careful because even though C is definitely 0, D is 0 as well here, which may not be obvious if you're just thinking of vectors. 4 charges lie on the 4 corners of a square with sides length A. What is the electric potential at the center of the square? So again, I'll give you a second. So the first thing you want to do here is you want to think about, okay, what is the distance it is from the center here for one of these charges? And so here you can say, okay, it's a distance, if this is A, this is A, you should be able to calculate, this distance. But it turns out that doesn't really matter because here, if you're right here in the center, this distance, it's a certain distance away. Let's say it's 1 unit, whatever it is. This would be KQ over 1. Okay, well this one would also be KQ over or K negative 1 Q over 1. So those would cancel, and these would cancel. Okay. That's 0. And so this is not obvious because this is 0 voltage, but is this 0 electric field? Well, a positive charge would be pulled this way and that way, so that would be, a positive charge would be pushed this way and that way, but it would also be attracted this way and that way. So a positive charge would have an electric field moving down. So the electric field at this center point is straight down. So the voltage is 0 here, but the electric field is not 0. Okay, so you have to be very cautious because again, this is not vector. What is the electric potential at the point indicated on the figure below? So it's again, if you want, just go ahead and pause it, but I'm just going to go right in here. So this is a 3, 4, 5 triangle. So literally just stick the numbers in and add them up. So V is KQ over R. So K is 9 times 10 to the 9th. So you stick the numbers in with the positive and negative signs and just calculate it out. In this case, you get 140 volts. So, one is that. I mean, the distances and everything on there, I think it's a pretty straightforward thing, but hopefully that makes sense. And that looks like it for now. So that's the end of these notes. So I'm going to stop recording. There's also a audit that you guys should do today, and go ahead and ask questions onto the discussion board if you have questions, and I'll see you all next class.